Well, good afternoon, or I should say good evening, students. It is after 8 o'clock here, Sunday, November 24th, the Sunday before Thanksgiving. We're going to do another Mr. Rich Q&A. We have a very light crowd tonight. I kind of figured that, as most of my students are already on their break for Thanksgiving, as St. Johns County schools don't have class tomorrow, although Duval County does have class on Monday and Tuesday. What I wanted to do today is do a little bit of work from both Algebra 2, Pre-Calc, and Calc. I do have one question, at least one question from AP Calc that we can work on. But before I get to that, I did want to start in on some Algebra 2. So let me pull up my screen and show you what I have for tonight. What Algebra 2 is doing, most of my Algebra 2 students are doing polynomial division. So I wanted to work through some polynomial division where we are dividing polynomials by linear binomials. Here is what that looks like. I'm going to show you an example of a long division problem where I'm taking a trinomial here and dividing it by a binomial. So here's what the long division process looks like. I'm not going to go very slow through this, but I'm going to show you how it looks. I'm going to divide the m minus 5 into m to the third minus 12m squared plus 33m. And I'm going to add the missing term here of 0, right? There's no constant term here. So any missing terms, any exponents that are missing, you have to fill those in with a 0. For example, if you take a look at, there's a problem here that's got a missing coefficient. I shall show you what it is. If I were to do this number 10, notice there's not an x squared term. We have to account for all of the exponents on the variable. So we would have to tuck in here a 0 times x squared in between the x cubed and x as I'm doing that division. In this problem, there's just missing a constant, so I'm sticking a 0 on the end. Here's what the polynomial division looks like. I'm going to divide the two leftmost terms to get the ball rolling. I'm going to take m to the third and divide it by m. I'll do that off to the side here. M to the third over m. I subtract the exponents, right? And I get m squared. So that's my first answer here. The first part of my answer is going to be m squared. I then take the m squared and multiply it by the binomial and put the result underneath my polynomial here. M squared times m is m to the third. M squared times negative 5 is negative 5 m to the second power. I'm then going to do subtraction. And here's where most of the mistakes are made. If you take m to the third minus m to the third, they cancel. This should always be a 0 right here. Next, I've got negative 12m squared minus a negative 5m squared. That's negative 12 plus 5. That is going to be a negative 7m to the second power. Right, the common mistake here would be to add those and call it negative 17m squared. No, negative 12 minus a negative, which means minus 12 plus 5m squared. We next bring down the following term, 33m, and we repeat the process that we started with. We're going to divide the negative 7m squared by m, which would give me negative 7m. I'll now multiply the negative 7m times the binomial, so I get negative 7m squared and a plus 35m. I am doing subtraction. These cancel, but 33m minus 35m is negative 2m. Bring down the 0. Repeat the process. Negative 2m divided by m is negative 2. That gives me a negative 2m plus 10. And then I do subtraction and I get a negative 10. This is the remainder, right? There's nothing else to pull down from up here. So it is the remainder, but then that means that I'm going to put a minus 10 over the divisor and minus 5. And this expression is the answer to the division problem right there. I want to show you what this looks like with synthetic division. If I do synthetic division here, what we do is we pull the coefficients off of this polynomial. It's a 1m to the third minus 12m squared. Then there's a plus 33, and then there was a 0. Now I am dividing by m minus 5, so I am going to change the sign of that and make it a plus 5. And I'm leaving a blank row right in here. What I do for synthetic division is so much faster than long division. I bring the 1 down and then multiply and put the answer right here. 5 times 1 is 5. And then I do addition, not subtraction. Negative 12 plus 5, negative 7. 5 times negative 7 is negative 35. I add, I get a negative 2. Multiply, get a negative 10, add negative 10. This is my remainder. That's my constant term. That is my first degree term, negative 7m. And then there's my m squared. M squared minus 7m minus 2 minus 10, my remainder, over m minus 5, like that. It's so much faster. You wonder why you would even bother with long division. Well, if you've got a polynomial divided by a linear binomial, you probably don't want to do long division, okay? There is another trick if you've got a binomial, a linear binomial that has a coefficient that's not equal to 1. So that, I'm not going to show you how that works. Some of your classes will cover that. Most of them in St. Johns County, I don't think are even going there. You probably don't have to worry about that until maybe pre-calculus. However, if you were dividing by, say, a quadratic or like a quadratic trinomial, then synthetic division is not the way to go. You have to use long division in that case. All right. Now, there was one question that did come in by a student who I don't think made it on here tonight, but I am going to work one of the problems for her. And it was a problem from this unit. And here is what the problem was asking. It gave a question that said, it says this: is x minus 2 a factor of, and then it gave a n of x is the polynomial. It's x cubed plus 2x squared minus 6x minus 4. There's two ways to answer this question. If x minus 2 happens to be a factor of that polynomial, then when I divide this binomial into that polynomial, if it's a factor, the remainder should be 0. That's what it means when you do division and the remainder is 0. It means the thing that you were dividing by is a factor of the thing that was being divided, right? So I know that 4 is not a factor of 7, because when I divide 4 into 7, I don't get a remainder of 0. 4 is not a factor of 7. So what I'm going to do is I'm going to quickly do synthetic division. I'm going to pull the coefficients here, 1, 2, negative 6, negative 4. I'm going to divide by 2. So I change the minus 2 to a plus 2, pull the 1 down, 2 times 1, add 8, 2. 2 times 2 is 4. The remainder is 0. So yes, it turns out that x minus 2 is a factor of this. In fact, I could write it in its factored form. It must be x minus 2 times x squared plus 4x plus 2, right? Because this would be my constant term. That would be the x coefficient. That would be the x squared coefficient. So when the remainder is 0, it means you really successfully factored the polynomial. There's another way to do it, which is not better than this one, I don't think. But if x minus 2 is a factor, it means that x equals 2 has to be a 0. So if you were to calculate n of 2, you're going to get an answer of 0, which tells you that 2 is a 0, meaning it is a factor. Okay, that's all I'm going to say about that. So that is polynomial division for the Algebra 2 students. Want to do a little bit of work on logarithms for the pre-calc students, because you are into logarithms. Most of you are already into lesson 2.12, which is logarithmic function manipulation. This is where we are compressing and expanding logarithms. And the properties of logarithms that we're using in this unit are the following: that if you have the log of two things multiplied, 2 or more things, you can split them out into their separate logs, separated by addition. So it would end up looking like that. Log of A times B is the log of A plus the log of B. The other one that goes along with that would be the quotient rule, where we do log of A over B. And when you have division inside the argument of your logarithm, you can split it out into separate logs by subtraction. So that would be log of A and then minus log of B. The third one is log of A raised to the power of B. And that means that I can bring the exponent to the front of the log as a multiplier, like that. So when we go from left to right, as I've written these rules, it's what we call logarithm expansion. I'm taking a singular log and expanding it into, in this case, 2 logs, but in this case, a log multiplied by a constant. If you go in the opposite direction, you are condensing the logarithms, taking a log and simplifying it using those properties. Let's see how this works. Here they want you to write an equivalent expression using a single log. So we are condensing the logarithm. So I can condense these 2 logs into 1 log by using the addition property in reverse, right? I'm condensing it into 4 times z inside of a single logarithm. This one, I'm going to do the same, but before I condense into a log, I'm going to take this 3 and move it into the exponent. So this would be log base 4 of 6 plus log base 4 of x to the 3rd power. Now I can condense this into one singular logarithm, log base 4 of 6x to the 3rd power. That's condensing logarithms. Let's try number 9, a multiple choice problem. This says, which of the following is equivalent to this expression? There's 3 separate logs here. The first thing that I am going to do is I'm going to take each one of the coefficients and take them up into the exponent. So this first one would be log of x to the 3rd minus log of y to the 2nd plus log of 16 to the 1/2, which would be 4, right? 16 to the 1/2 would be the square root of 16, or 4. So I'm going to condense these into 1 log. Now, the logarithm that has the minus in front of it, that's going to go down to the denominator of the one singular logarithm. The ones that have a plus in front of them, these 2, are going into the numerator. So the singular logarithm will be the log of 4x to the 3rd over y squared. So go with answer C right there. All right, let's move on to 2.13. And this is where we're going to be solving exponential and log equations. Most of the students that I'm working with, I don't think their classes have made it all the way to lesson 2.13. So we're working a little bit ahead here. So I'll solve a few exponentials and a few logs. And this is where we're using logs and exponentials as inverses of each other. So what I'm going to do when I solve an exponential is I want to isolate the exponential. So I am going to subtract 4 on both sides. And in order to get rid of an exponential, I'm going to use a logarithm. And the logarithm that I'm going to use is the logarithm that has the same base as the base of the exponential. That's how to use these inverse functions to solve equations. So I'm just going to take log base 3 on both sides of the equation. Now, why would I do that? Well, because one of the properties of logarithms that we've looked at in prior lessons in Unit 2 is that when you have a match between the base of the log and the base of the exponential inside the logarithm, they, in a sense, cancel each other out, leaving you the exponent. So right there, I freed my exponent up, and it's just x equals, and this is my final answer. Log base 3 of 11. Now that is an irrational number. If I wanted to know what it is approximately, I can always go to my TI-84 and run math log base and tell it log base 3 of 11, or ask it log base 3 of 11. It'll give me this irrational number. But this is going to be my exact answer right there. Okay, let's try this one. All right, same thing here. I'm going to add 7 on both sides. So I'll get 4 raised to the x plus 3 is 9. I'm going to take log base 4 on both sides, leaving me just the x plus 3. I'm going to get log base 4 of 9, and then I have to subtract 3 from both sides. So my final answer is log base 4 of 9 minus 3. So This minus 3 is not inside the argument of the logarithm. Just to be sure, you can put that in parentheses to clearly indicate that that's the only part of the argument of the logarithm is the 9 right there. Okay, let's go down and solve some log equations. Well, my variable is captured inside of a log. I need to get rid of the log, so I am going to use an exponential. I'm going to do something called exponentiate. I am going to raise to power on both sides like that. Because when I have 2 raised to the log base 2, they cancel and it leaves me just the argument of the logarithm. And then solving, I get x equals 9. Now, when I solve a logarithm equation, I always want to go back and make sure that when I take this solution and plug it back into the log, I do not get a number that's not within the domain of logarithms, right? The domains of logarithms are x greater than 0. So anything that would give me a 0 or a negative inside of the argument of a logarithm is not a valid solution. 9 is going to be okay because I get a positive inside my logarithm. Here I'm going to raise 5 power. I'm going to exponentiate with a 5 on both sides. This gives me 2x minus 1 is equal to 5 squared, or 25. So 2x is 26, x is 13. That answer is valid. It checks. Here I'm going to, so this is a natural log, right? So don't forget, what in the world does ln stand for? It is a substitute or a shorthand for log base e. That's all that it means. So if I multiply both sides of this by 3, I get 12 is equal to the natural log of x plus 5. Well, I'm going to exponentiate with the base of the logarithm like I did in the previous 2 problems. It's just that the base here is the natural constant e. So I am going to exponentiate with e on both sides. This gives me e raised to the 12 is equal to x plus 5. And so my answer is e to the 12th minus 5. That is my exact answer like that, because this is an irrational number. So any answer that I give as a decimal would be an approximation to an irrational number. So that is how I solve for x in that case. And let's do a few of these. This says to use the log properties to help solve the following equations. Using exponentials to solve these logs was a great way to do it because I only had one log on one side of the equation. So I could get rid of that log through just exponentiating with the base of the logarithm. Now over here, before I'm going to take the same tact here, but I have to condense logs where I can. Right? I can't really do anything here until I combine these 2 logs into 1. So I'm going to do log base 3 of, and when I condense this, right, when I condense 2 logs that are separated by minus, the argument is going to be with division. So it's going to look like this. Now I can exponentiate both sides with a 3, or just use what we call, I think they call it the one-to-one property, right? The only way this equation can be true, since I have a log base 3 on both sides, is if the arguments are the same. So I'm really just dropping the logs. Or think about it this way, exponentiating with the 3, yeah, it will leave me 2x minus 1 over x plus 3 is equal to the number 4. I will multiply both sides by x plus 3. That's going to give me 4x plus 12. I will subtract 2x from both sides. I will subtract 12. I'm doing this super fast, but it looks like my answer is negative 13 halves if I did my math there correctly. Yeah, that looks good. Oh, and of course, we have to make sure that that's a valid solution, right? If I take this, which is actually, what is that, negative 6.5, I don't think that that's a valid solution because it's going to give me a negative number inside that logarithm. And since it was my only solution, I would conclude that there's no solutions to this problem because this is what we call an extraneous solution. When I plug it into both of these logs, it's going to give me a negative on both of them. Let's try one that results in a quadratic, right? So this one here, when I get rid of the log base 2's on both sides, it just leaves me x squared minus 4 is equal to 6 minus 3x. So it looks like it's a quadratic. we'll gather the terms on the left side and then factor the quadratic. I'm going to go with plus 5 minus 2 as my factors, which means I have x equals 5. Let's go with negative 5, right? And positive 2. And I don't like negative 5. No, I do like negative 5. That's going to be perfectly fine. That'll be a positive number. That would be a positive. If x is 2, that's no good. I cannot take log of 0. Log base 2 of 0 does not exist. So 2 is an extraneous solution. Bye-bye. Only one solution, x equals negative 5. Let's do some more that come out of 2.13. These are evaluating logarithms without a calculator. And so what I want to do here is I want to try to match, if I can, the base of the logarithm to the base of the exponential inside. So here's what these problems would look like. I know that 27, oh boy, let's do it this way. I can't write 27 as a power of 9, at least with an integer. So one of the ways that I could do this is I could let this be equal to x and then exponentiate on both sides. I get 27 is equal to 9 to the x. I could write this as 3 to the thirds, this as 3 to the second to the x, which is 3 to the third equals 3 to the 2x. Now this, with the one-to-one property, 3 has to be the same as 2x, so x is 3/2, like that. This one's a little easier because I can express 36 as a power of 6. This is, I would do this in my head, but I'm just writing it out here so you can see it. It's log base 6 of 6 to the second power. Those cancel each other out. I'm left with an answer of 2. This is an obvious answer of the number 4. And let's try number 7. I'm going to rewrite this as log base 9 of 3 to the minus 1. Can I write that? I think I can rewrite 3 as the square root of 9, right? So I could do log base 9 of the square root of 9, right, which is 9 to the 1/2, that's what 3 is, to the minus 1, which would be log base 9 of 9 to the negative 1/2. So this has to be a negative 1/2. All right, so you'll get lots and lots of practice on that. Then there's some using properties of exponents to solve the following equations where I've got exponentials on both sides of the equation. So I don't think we're going to get into that, but I do want to go over to Taylor's question. She has a question she sent over involving the mean value theorem for calculus. Let's see what this looks like. Number 1, it says selected values of a differentiable function f are given in the table above. Oops. What is the fewest possible number of values of c in the interval 1 to 9 for which the mean value theorem guarantees that f prime of c is 6? That's a good question. What I am looking for are average rates of change that would be equal to 6. So I'm going to look at all possible combinations here. If I look at these first 2 points and I calculate the slope, right, which is the average rate of change, that would be 42 minus 0 over 9 minus 1. That's not 6. Okay, so let's go from 9 to 3. That would be 36 over 6. So anyways, that looks like I definitely have 1, right? The average rate of change from 3 to 9 is 42 minus 6 over 9 minus 3, right? That's what I would call the average rate of change from 3 to 9, which is 6. So that's at least 1. So A is out. Let's go from 9, from 5 to 9. So that would be 42 minus 18, which is 24 over 4. That's a 6. So the average rate of change from 5 to 9 is 42 minus 18 over 9 minus 5. That's a 6. So now we're down to either 2 or 3 as our answer. If we go from 9 to 7, 7 to 9 right here, that's 13 divided by 2, which is not 6. Let's look at these other intervals right here. 6 minus 0 or 3 minus 1, that doesn't work. How about from 3 to 5. That's 12 over 2. 18 minus 6 is 12, or yeah, so it looks like 3. That's because I got at least 3. So I can stop right there, and that's my answer. I hope that helps, Taylor. I think the key there is checking all of the possible intervals where you could calculate an average rate of change. Because remember, the mean value theorem says that you're looking for a place where f prime of c is equal to the average rate of change over the interval right there. So there's a bunch of intervals to check there. We found at least 3, so we can stop right there. You are welcome. Glad we could help there. Anything else, Taylor, that you want to go over? We've got time here for some AP Calc. Okay, very good. Let's do, though, a little bit more on the calculus. We did some of these in the previous session. What I'm going to do, Taylor, if you're still with me, or those of you that are watching that are in AP Calc, I'm going to go over the extreme value theorem. Students, this is how we find what we call absolute extremes on a closed interval. So here is the step. Here are the steps. It says to find the extrema, that means the absolute highest and absolute lowest values of a function. To find extrema of a continuous function on a closed interval a to b, use the following steps. First, we have to find the critical numbers of the function that are within the interval in question a to b, and using just the open interval. And that begs the question, well, how do we find critical values? Well, critical values are found by taking the derivative of the function and finding out the values of x that make the derivative 0 or that make the derivative undefined. Then we're going to evaluate the function at each of the critical numbers. We're also going to evaluate the function at each of the endpoints of our closed interval. And then the least of those values is the absolute minimum, and the greatest is the absolute maximum. And notice what's said here. So this is often called the candidates test. Your teacher may refer to this as the candidates test for absolute extreme. Because what you're going to do is you're going to come up with the candidates within the interval at which the function has its highest or lowest y value. And the candidates are simply the critical values that are in the interval and the endpoints of the interval. Now, when we work one of these problems, if this doesn't make sense to you as to why those have to be the locations where we would have the absolute highest and lowest y value, once we do the first problem and we graph it, I think it'll become pretty apparent. So anyways, let's work a problem and see how this is going to work. We'll stay away from the trig on this for now. Let's try this one. This says finding the minimum, maximum velocity and acceleration. This problem says that a particle moves along a straight line with this function over the closed interval 0 to 3. Find the minimum and maximum velocity of the particle on the interval 0 to 3. All right, this is the position, so we need to get the velocity function. The velocity is the first derivative of the position. That would be 4t to the third minus 12t squared plus 12t. And what I want to do is I want to find the critical values for the velocity, okay, because I'm trying to find the min and max velocity. So what I have to do is I have to find the critical values for velocity, which means I need its derivative, which would be 12t squared minus 24t plus 12. And I know that's the acceleration, but for us, it's just, if I'm trying to find the max and min of the velocity, I need to know its critical values, which are where its derivative will be 0. So this is a quadratic that can be easily solved because I've got a common factor of 12 that I will pull out. It's going to leave me that right there. That can be factored into t minus 1 squared. So t equals 1 is the critical value. So now I make my list of candidates. So that is the critical value of v of t. It's not the critical value of v prime. It's the critical value of v because it's the t that makes the velocity derivative equal to 0. So now my candidates are the following t values: 1 and the two endpoints, 0 and 3. Okay, let's put them in order. 0, 1, and 3. What we need to do is find out at those candidates, what is the velocity? Well, the velocity at t equals 0, when I stick 0 back into my velocity function, it will be 0. When t is 1, it's going to be 4 minus 12 plus 12, which would be 4. And then I'm going to stick 3 in. Let's see if I have the answer key on this, or we can just do it by hand. So when I stick a 3 in, I'm going to get 4 times 3 cubed, or 27, minus 12 times 3 squared, plus 12 times 3, which is 36. Okay, I'm going to pull up the answer key so we can maybe go a little bit faster on this. So we got 0, 4, and then this is going to be 36. So where's our minimum velocity? This is our min, and that is our max. So what we can say then is the minimum velocity over the interval 0 to 3 is 0 at t equals 0. We can then say our maximum velocity over the interval will be 36, and that occurs at t equals 3. I want to show you what this looks like on Desmos. Let me reset my Desmos here. We're going to plot the velocity, 4t to the third minus 12. I'm going to use x to remind you here. 4x to the third minus 12x to the second plus 12t plus 12x. Okay. Oh my gosh, that's not going to work. 4x to the third, 12x squared plus 12x. That's not going to work either. Plus 12x. Okay, there we go. All right, let's scale this a little bit better. So on my x-axis, we're just going to go from 0 to 4. All right. So we see that. What I'm going to also do here, class, I'm going to go ahead and plot vertical lines at x equals 0. That shows the boundaries of this thing. So I've plotted the locations here, the closed interval from 0 to 3. So yeah, you can see that the lowest value is over here at 0. The highest value is up here at time t equals 3, which is a 36. And perhaps you can see why we're looking for critical values in the interval. Because, well, let's just suppose I'm going to draw on this and just give you some examples of what a function could look like. Let's just suppose that we had a function. Let's turn this thing off. I think that might help. Yep, okay. Okay. If my function did something like this, notice these would be the endpoints. Those are two candidates. This would be my relative max. So this would be my critical value where the derivative was 0. These are my two endpoints. So it looks like my max is going to occur at the critical value, and my min is going to occur at one of these down here, whichever it is. Now, let me show you this. Suppose that you had a function that looked like this. Notice my absolute minimum value occurs at the first endpoint on the left side of the interval. This is neither a min or a max, but look it up here. This is a critical value. If this function is f of x, at that location, f prime of x is undefined. It's not differentiable right there. Okay, it's not differentiable. Now, look at the criteria here. Let me go back and show you what we're looking at here. Notice it says that, it didn't say that it's differentiable. It says to find extrema of a continuous function. So this function is not differentiable, although it is continuous. So that's why here we're actually looking for critical values where the derivative would be undefined. Because if the derivative is undefined, then it could be a location where you have this, in this case, a cusp, which is going to be the absolute maximum value. So critical values, again, are going to be places where the derivative is 0 or where the derivative is undefined, so long as that undefined location is in the domain of the original function. All right, so it's only the only place on a closed interval that you're going to find the highest and lowest y values are going to be at the endpoints or at critical values that exist within the interval that you're examining. Okay, and that's called the extreme value theorem. One of the common mistakes that students will make on a problem like this is they will see minimum and maximum, and they will think that they are required to do a number line test where you plot the critical values on your horizontal axis and then pick values of x to represent the intervals created by the critical values. But you don't need to do that on an absolute extreme. All you need to do is find the critical values, make sure that the critical values that you found are within the interval, in this case between 0 and 3. If they are, if one of them is, or two of them are, however many critical values are within the interval, those get added to your candidates list. And then, of course, your candidates are also going to include the endpoints of your closed interval. And then you evaluate your original function at all of those candidates and find your lowest and highest. It is possible for there to be a tie, right? So you could have a location where there's a min at two different t locations because it's the exact same value. So that's possible for there to be a tie at two locations or three locations even. But at any rate, that is how you do the extreme value theorem, finding absolute extremes. Well, I think we'll cut it off there. We're a few minutes shy of 9 o'clock, but we'll leave it there. Next Sunday, which would be the 1st of December, I will be here again for a Mr. Rich Q&A, and we'll get you ready to get back into school for the last 2 weeks before the winter break. All right, everybody, have a wonderful Thanksgiving. Have a great time with your family. Relax. Don't worry about school. Take some time off, refresh yourself, and then get ready to get back to work next Sunday, and I'll see you then. So long. Thank you, Taylor.